Welcome to my talk titled Supporting Collaborative Modeling via Natural Language Processing. I am Başak Aydemir from Boğaziçi University, Turkey, and the paper I'm going to present is the result of our joint work with Fabiano Dalpias from Utrecht University, the Netherlands. This is the long version of our presentation. In the description box below, I'm going to link the slides for this presentation, as well as our summary presentation and the corresponding slides. So our motivation for this work comes from collaborative modeling settings where multiple experts work on the same solution from different perspectives. So depending on their perspectives, such as security or safety, they might use different modeling languages. In many scenarios, these experts are located in different locations and they work in different time zones. One example is designing solutions for European air traffic management systems, where European experts from different countries work within their own locations for their perspectives, and then they organize physical meetings to align their models, discuss solutions, and negotiate. The problem is that the experts' time are quite expensive. It's difficult to find a suitable time slot, and in the time of a pandemic, it might not even be possible to bring everyone together. So our solution to this problem is to design a web-based service to help model alignment and model completeness. The service does that by providing suggestions to the models when the modeler asks to get some suggestions, and a suggestion is a set of concepts to be included in the model. So what might be the next thing to model? You can think a suggestion like this. The service is agnostic to the modeling languages, so it's quite easy to add a new modeling language. There is no need to spend time and effort on meta-model alignment. It is also not interested in the model structure, so you do not need to share the whole model, but just the textual labels. The service analyzes these textual labels. A textual label can be the comments or entity labels or relation labels, and it keeps track of which concepts are included in the model. And once a request from the modeler arrives to the service to get some suggestions, the service identifies the missing concepts that are included in the project but are missing from that particular model. And with these missing concepts in hand, it consults the domain model. It finds some matches from the domain model based on the missing concepts that might be relevant to the model. It filters the candidates and provides a set of suggestions to the modeler. It's up to the modeler to include these suggestions into the model or not, and if the modeler wants, he or she can provide some feedback about the usefulness of this model. So this diagram shows the inner workings of our model. So here you see that it starts with the model being committed. A commit is a significant change in a model. So whenever the modeler thinks that there has been a significant number of changes in the model, it commits the model, therefore shares these changes with the service. The service analyzes the commits and basically it extracts the noun phrases, terms that are included or removed from the commit, therefore from the model. So in general, the service knows which terms are included in which model, but also what are the overall terms included in the project. Next, when a suggestion is requested by the modeler, the service checks the final stage of which terms are included in the project, and it identifies the missing terms from that model. With the missing terms at hand and with the domain model, the service finds some matches, tries to find the most suitable suggestions from the domain model, and send these candidate concepts to the modeler. So we rely heavily on natural language processing for extracting terms, but also identifying missing terms and exploring and finding matching from the domain model. What is not shown here is the feedback part, where the modeler sends feedback about the usefulness of the suggestions, which service then uses this feedback to customize the future suggestions. So some heuristics that we use in our natural language processing operations. So one task is to find matches. So matches are imported in two different stages. So the first, to identify the missing objects, because some terms might be included in the model, but the other modelers might use a slightly different terminology in the project terms. So we do not want to provide some redundant matches. So it's important to identify the missing concepts well. And the second time we use matching is when we go and explore the domain model. Again, the modelers might use a slightly different terminology from the domain model, so we want to catch the similarities there as well. So here the strategies we show starts from the most strict strategy to the more flexible ones. So the obvious one perhaps is to have like an exact match. So here we just do a string search. So for example, if you have a term like thesis, a possible match is the term thesis. If you want to get some flexibility, you can look for a substring match. In this case, a suitable match for the term thesis can be thesis project. Next, you can look for similarity and relatedness. So for similarity, a thesis project might be a synonym in our domain model as for graduation project, so that they are very similar. You can play with the threshold for similarity, of course, or you can look for the terms that co-occur quite frequently. In this case, you are looking for a relatedness heuristic, and with thesis, perhaps a coordinator is a frequent co-occurred word. So that might be a suitable suggestion. Next, when you find some matches, you actually decide what to suggest from the domain model. So in this case, you see a domain model here. This example is taken from the Business Informatics Master Program of Utrecht University. So we scanned the website and we built the domain model basically from the information shared over there. I do not expect you to read this model. I will zoom in a bit. But the idea is, once you find matches in your domain model, which term you are going to suggest? That's the question. So in this case, the three strategies we adopt is like if some general term is missing, actually, in this case, you can suggest the parent of the match. You can always suggest the match itself, of course, but apart from that, you can suggest the parent of the match. If you want to add more detail, you can suggest the child of the match, or if you want to branch out a bit, perhaps add some creativity or explore the horizons of the models, you can suggest its siblings. So here, consider that we have the first phase as a match here. So if you suggest the parent, you might suggest phase, or if you suggest a sibling, you can suggest like phase 2 or second phase, or if you look at the related ones or childs, perhaps you can look for like 3 months or problem statement. Next, you might have too many candidates for suggestions, and then you need to apply some techniques. Here, some basic heuristics you can apply is to get a fixed number. Perhaps like the first 5 candidates will be suggested, or you can incorporate the user feedback heavily. Or prune some of the domain model, for example, never get suggestions from those parts. You can look at the frequency of the suggested concepts and start suggesting the most frequently used concepts in the domain model, or you can select like different matches to make suggestions, but then you limit the suggestion per match and so that you provide a broader selection for your suggestions. So these were the heuristics that we incorporated in our natural language processing pipeline. But one observation we had was the heavy use of compound nouns, actually. So compound nouns were really present in the models that are integrated with working with our service, but also in the domain models we work with, there were many compound nouns. And when we apply our heuristics, we look at the similarity, for example, in order to identify the missing concepts or like the domain model matches. We had to deal with the similarity of compound nouns. So at this point, similarity analysis or metrics for for single words is more advanced than the similarity of compound nouns. So we decided to develop two algorithms to calculate the similarity of a pair of compound nouns. So the first algorithm we developed is based on WordNet and Word2Vec, and the second algorithm makes use of a domain model and calculates the similarity of two models using a domain model that they come from. So in the first algorithm, what we do is that we start with two noun compounds. So our focus is on the compounds with two nouns. And for each compound, we get the what we do is that we get the Word2Vec similarity score for the individual words of the compound words. And if this score is higher than a certain threshold, we actually go and check whether they are synonyms. And in order to check whether they are synonyms, we consult WordNet and check whether they exist in each other's one of the possible synsets, depending on the meaning of the noun. Then, if they are synonyms, we set this value to 1 and leave it as otherwise. Once we do this calculation for individual nouns, we switch to calculating the overall similarity score for compounds, and this is just an average of these individual values. I hope my explanation will be better with the example. So here you see two compounds. So one is the thesis project and the second one is graduation project. So in order to calculate the similarity of these two compounds, what we do is that we calculate the similarity of thesis and graduation, so the first words, and then project and project, so the second words, then thesis and project, and finally project and graduation. So what we do is what the sim function returns is either the similarity score from Word2Vec or 1 if they are synonyms. Then the task is actually to get the weighted average of this formula calculation. So I deliberately left out the numbers here, but you can check our papers. We did some optimization based on a gold standard that we have, but there needs to be more studies in order to optimize the weights that we have found. But basically that's the idea. The second algorithm we developed is a domain model-based similarity. And here the idea is that how well the compounds are matched in the domain model. So we go and search the domain model and try to find matches for each compound, again using the individual nouns as well. And then we identify the individual matching scores for each compound that we are comparing. And the similarity scores of these compounds are the average of their matching scores from the domain model. So in order to evaluate the performance of our algorithms, we have devised an experiment basically. And for this experiment, we came up with 20 pairs of two-word compound nouns. And we surveyed people and asked them to assess the similarity of these pairs. We collected the results. Their assessment was on a 5-point scale, and we basically take at the end the average for the similarity scores. And this was our gold standard. We compared this gold standard with our two algorithms, as well as BirdWeb and Spacey, which are publicly available off-the-shelf natural language processing libraries or frameworks. So here you can see the pairs that we use. So there were 4 categories basically. In the first category, the crosswords were similar. So the second word of one compound was the same with the first word of the second compound, so thesis project and project facilitator. In the second category, their first words was exactly the same, so first phase, first supervisor, second phase, second presentation. In the third category, their second words were the same, so first supervisor, second supervisor. And in the fourth category, none of the words were actually the same. Here are some example results. So our data is available. There's a link in the paper. You can check the full results from there. So for example, our domain model from this 20 pairs found computing science and information science pair is the most similar, or the highest similarity score, whereas in our gold standard people said official ceremony and graduation ceremony pair has the highest similarity score. And the bottom part of this table is actually for the least similar pairs. For the domain model, it was like first phase and like first supervisor. For WordNet and word embeddings, so word-to-vec algorithm, it was MBI thesis and like thesis topic. And for gold standard, people thought first phase and like first supervisor, or MBI student or student administration pairs are not similar that much. So here you see the results based on categories. So the last one for each category is the gold standard, and the first one is our word-to-vec and WordNet solution. Then SPACY, domain model, and like BirdWeb. Here you can already make some observations, but it's still difficult to make with the naked eye. So when we look, perhaps for some categories, BirdWeb is quite similar to the gold standard. For some others, it's not. So that might be one observation that you already make. But when you do some analysis, we saw that the SPACY has the highest Pearson correlation with the gold standard. On the other hand, domain model-based solution has the least Euclidean distance. So actually the vectors of the results were the most similar to the gold standard. So it produced the similar results to the gold standard. So for different categories, we see that also for like BERT has some promising results as well. So what are the lessons we learned, or some take-ons, our observations from this work is that natural language processing can be used to support collaborative modeling activities. So our hypothesis is that our service in the long run would help people to align their models better, have a better coverage, and perhaps move to a completeness of the models, and it encourages using a common vocabulary. But there might be other creative uses of natural language processing for collaborative modeling activities. Conceptual modeling domain also brings some own challenges to the natural language processing. So we do not always deal with some certain sentences. We have lots of jargon, so generally trained natural language models perhaps may not work the best for our cases. I think the indication that our domain model-based solution really resembled the gold standard because our people whom we surveyed was very familiar with the domain, so they were the students of that master's program. So having a domain model, I think it helped to resemble their opinions. So that might be the case, and also like the compound nouns is a specific challenge, I think, for the for NLP libraries. That being said, it's difficult to be conclusive because we are aware of the low sample size, both in terms of the similarity, like the survey we did, so our gold standard is not that big, but also in terms of pairs, but also in terms of participants. So we need to think about more and like make more empirical evaluation of our work in order to have more like definite results. But it's a promising area that is worthy of checking. So in conclusions, we provide a lightweight natural language processing power service to facilitate collaborative modeling. Our service is agnostic of the modeling languages, so there is no need to align meta models, but we focus on keeping track of what is included in the models, and our aim is to cover the same domain, so we want the terms to be as similar as possible in different models. We applied different heuristics for matching, for filtering, for deciding on suggestions. And for this work, we observed the challenge of finding similarity of compound nouns and worked towards to calculate the similarity of them, and our focus was only on the two-word compounds. Obviously there are longer compounds with 3 or 4 words, so that's also requires some attention from the research community. With our algorithms, we observed that our domain model-based solution performed the best in terms of Euclidean distance, so it's resembled the gold standard the most, but we need more empirical evaluation in order to be more definitive and conclusive in that sense. Thank you for listening to my talk. So this was a long presentation. I will provide the link to the slides below, and if you have any questions or comments, we would love to get in touch with us. So these are the communication information of me and Fabiano. Again, thank you for attention, and I hope you check the paper.